Okay. To introduce Professor Chelsom, I have a privilege knowing him for over 30 years, I think. And he started, when he finished his PhD at City University of London, I was just starting to work there. And that's how I know him there. And also I have the privilege to know John Chelsom Sr., who was my colleague at City University. John has got his bachelor degree from the University of Oxford, his PhD at City University, and now he's also the adjunct professor at University of Victoria, you all know, and also City University in London. And he has done many consultancy around the world, and including World Bank in area of telemedicine. And in his commercial life, John, in 1990, he had a company called CSW, which was a key player in national program IT for NHS in England. And some of his software was key components in terms of implementing the summary care records in London, in UK. So he has got a long experience in area of health informatics, and we are grateful to have him here, as usual, every year to give us his talk on the area of structured health record as the foundation of artificial intelligence in medicine. So I think his bio is there more extensively. You can read it yourself. Without further ado, and I just like John to start his talk. And thank you very much again,
John. Okay, thank you, Abdul. Can you hear me okay?
Perfect, thank you.
Okay, good. Thank you for the intro. Normally, Abdul is the best introducer of me ever, although he said that we'd known each other for 30 years, so I think we could strike that out of the introduction next time, so we must be very old, both of us. But I'm going to talk about particularly using structured electronic health records as the basis of AI in medicine. I've just been busy hacking around with my material to make it fit in an hour, so I'm not quite sure what I'm left with, but I'm pretty certain it's not going to follow the agenda that that's listed there. But we'll see where we go, and we'll keep going till an hour's up. Then if you want to stop and ask questions as we go along, that would be fine. I'll try not to divert too much, but also leave some time for discussion at the end as well. So I think the general reason why I like to talk about structured health records is that I've been working in artificial intelligence for quite a long time. And at the time that I started in the mid-1980s, it was just at the very beginning of Bayesian belief networks and artificial neural networks, like right at the start. So most of the AI in those days were based on the same sorts of techniques that had been used since the 1950s. When I finished my PhD, which was about 1990, I moved out of AI, but AI kept trundling along without me. And it sort of moved along reasonably slowly until maybe 10 or 15 years ago. And we've had a sudden explosion, or recent explosion in interest in AI. Most of the interest in artificial intelligence now is about machine learning and pattern recognition based in some form or other on neural networks. those techniques are particularly well suited to working with unstructured information and spotting patterns in it. And a lot of them are very useful, and we use them in our everyday lives for recognizing faces and telling Alexa what to play next and all that sort of thing. But at the same time, we've been doing that in AI in the field of health informatics. We've sort of, in a sense, been moving in the opposite direction, because there's been a big push in the last 20 years to make structured information for electronic health records. So whereas we combine unstructured information with AI, so as we produce more structured and coded electronic health records, then we ought to be able to do more with those structured records than we can with unstructured data. So it's not to say that unstructured data is not helpful and useful. It's very useful, but the sorts of things which we can potentially do with structured health records are at least as valuable and potentially more valuable than some of the most recent machine learning type of activities. So the purpose of today is just to look at how we're structuring electronic health records and standards for doing that, and then some of the doors that opens for artificial intelligence, all in an hour and as far as we can get. So I'm pretty sure things I'm probably not going to talk about, the two at the end, which are Bayesian belief networks and artificial neural networks, and sort of on the basis that those are things which probably people are most interested in outside of what I might say today. Okay. So we'll just start with how we make structured health records, in particular the two main open standards for doing that, which is the ISO 13606 standard and the HL7 CDA standard, and we'll see how they're related as well. So just first to put that into context right at the beginning, then in healthcare we working with data as health informatics professionals, and if I look at the data on the left there of 1, 2, 3, 4, 5, 6, 7, 9, 0, total hit, t-score, minus 2.5, those are all data items, pieces of data. If I put those data into context, then I've got some information. So when I get information of the patient with ID that has a total hit t-score of minus 2.5, then I've got a piece of clinical information. And then typically in the structured electronic health record space, that would be called a clinical statement. So when I put data into context, I get some information. And most of the time these days people talk about data and they actually really mean information, so we'll excuse everybody for that, and also the fact that data is plural, and I shall break all the rules which I haven't set there but just mentioned. So let's start thinking about structured electronic health records. So actually the history of organized structured records in any form is surprisingly short. So it's only at the turn of the last century when Henry Plummer at the Mayo Clinic started making what he called his paper dossiers, that we had any properly systematic, organized patient records, of course, in those days on paper. So that's not actually that long. You'd imagine we'd have been making organized health records for much longer. And quite a good lesson to learn from that, apart from marveling at the fact that it's only just over 100 years ago. This paper from 2008 is a study which is taking the structured health record from 100 years ago, and because it's organized and information is recorded in a fairly uniform way, it was possible to extract the data from the first 100 patients. So the first 100 patients at the Mayo Clinic who had their data recorded in this way, those data can be analysed and conclusions drawn from them today. So if we take the amount of health information which is currently being generated and roll that forward 100 years, in 100 years' time, or probably even 10 years' time, we'll have such a vast amount of structured electronic health data that we ought to be able to do some really valuable things with it. So if we're structuring our health record, then we've got a number of standards to choose from, and one which probably most people know is one called ISO 13606, which has a number of strands to it, and I'll talk about several of them as we go along. The first is that it has a model called the reference model, which is a fairly simple model of how an electronic health record could be structured, and it more or less matches the structure of the paper record, so fairly similar to Henry Plummer's structures from 100 odd years ago. So the ISO 13606 reference model starts from the basis of a EHR or an EHR extract, and that contains a series of folders, and in the folders are compositions, and the composition is the sort of basic container for the electronic information in the record. And each composition is split into sections, and the sections contain entries. The entries contain elements or clusters of elements, and the actual data for the electronic health record is embedded within the elements themselves. That's the basic model, and we'll see exactly what that means in practice in just a second. So that structure, we could call it a hierarchical structure. It's not quite, but it is a bit. We can trace back to work done in the 1990s, initially in Europe on the Good European Health Record, and then later on the Open EHR Foundation, which sits alongside the ISO 13606 standards. So the ongoing activity of this work goes on in open air, and every so often, 5 years or so, it stops off and the ISO standard gets updated. So there's actually quite a gap between them now, but the basic model remains the same. So the EHR extract is the electronic health record for one person. Then we've got the high-level organization, which could be by episode or by clinical specialty or anything else. So over the years, initially maybe 20 years ago, when I was developing electronic health records properly as commercial products for sort of the first time, say 25 years ago, then we did have fixed structures of episode-based records. And over the time, we've moved away from doing that and just used folders as a way to organize information on a much more dynamic basis, rather than make every composition belong in a folder, and certainly not every composition belonging in a single folder. So folders are just a high-level organization. Composition itself would be the sort of thing which you might see in a paper record. So it might be a set of laboratory test results, or a clinic note, or a referral letter, or a discharge summary. The things which, if you were having a paper record, you'd have in a piece of paper that you'd put in your folder in the filing cabinet. And then within the composition, we're into the realm of documents. So sections being clinical headings, entries are the clinical statements about observations, evaluations, or particular instructions for action in the process of healthcare. And then the entries themselves either contain elements, which are the information put in a little bit of context, and clusters of elements when we want to organize data perhaps in a table or some sort of slightly structured collection of data which belongs together. And the actual recorded values are in the data elements themselves right at the bottom level, which would have clinical coding and maybe measurements with units of measure, for example. So if we build an electronic health record system, here is one called CityHR, then in a well-designed electronic health record system, amongst many other things, it should be possible to identify on any particular view from which parts of that basic structure record and the ISO 13606 structure, where does everything come from? And this is particularly true of systems which are built in a model-driven way, as I'll show in a minute, which this system is. But if we take any view or piece of information in it, we can trace it back to the model that we just seen. So that whole screen is the health record, so the EHR extract of the EHR. And by setting a particular care setting, so here we've got a demonstration setting, but the care setting might be things like the specialty of care, so maybe rheumatology or liver and biliary and cancer, etc., as specialty areas. Or the care setting may potentially be an episode of care for a particular patient. Perhaps we're interested in a chronic condition, so the care setting may be their diabetes or a particular episode lasting a long period of time, say in their cancer treatment. So the care setting gives us some overall organization into what types of information we can see most readily. So it doesn't exclude information, but it helps to organize the information in the views. Now, down the left-hand side here, we have the compositions which are available in that particular care settings to enter as new data in a form. And the one that we picked there, the disease activity score, is being interacted with in the view. And the section, disease activity score DAS28, is the single section actually in this composition, which is displayed, which contains an entry. So that entry is the clinical statement, the lowest level of clinical context in the record, and it also corresponds to the view on the left-hand side, which is the image. So there's a link between an entry in the record and a graphical interaction with it, which can be set up. And basically, by clicking on the homunculus image, we can record tender and swollen joints, and from which the disease activity score is calculated. So in that layout of the disease activity score, then the count of tender and swollen joints themselves is in a cluster, and the individual elements are things like the disease activity score, which has a calculated score based on the other data that's entered and the number of tender and swollen joints, and the actual data itself is the recorded data item within that element. So any view in a system like this, we can identify from where in the base structured health record any of the information came from. So if we get rid of the noise, we can see the structure that health record is based on. So particularly important is the entry, so the clinical statement. So I've mentioned at the beginning that data on their own have no meaning whatsoever. It's only when we put them into some context that we get meaning. And in the structured health record, the lowest level of meaningful clinical context comes with the clinical statement, or the entry in the ISO 13606 model. So there's an entry for bone mineral density with a scan, a DEXA scan, and measurements of the bone mineral density for lumbar spine, femoral neck, and total hip, where those scores are clusters of elements with the data values as recorded. So that whole BMD, bone mineral density data, is a single entry in the ISO 13606 model as a single clinical statement. So of particular importance or interest is the context of, I've said that data without context is meaningless. So how do we construct this context and turn data into information? Well, we can take this view of the ISO 13606 model. It's not a view universally held, but it's the view that I like to think of. And it keeps the model nice and clean to organize it in this way. So from the bottom level of the data, we only get to any meaningful clinical context when we get to the entry level. So we have to have a certain amount of context for something to be clinically safe to use. So if we're passing information around or using it in reasoning processes, we need at least to be at the entry level, where we're saying the total hip T-score is whatever it is, or the diastolic blood pressure is. So we can't just say a value, we need to put it into minimal clinical context. The next place in the model going upwards where we get to some context is at the composition level, because we record all the entries in a particular composition at a particular time. So if we're filling in a form, at the point we press the button to commit those data to the record, or at the particular time that a message comes in from a laboratory system or an external system and appears in the patient record, that time is setting the temporal context, and that's recorded at the composition level for all the entries that are in that composition. That normally also sets some sort of spatial context, and the context of the origin, the provenance of the information that's in that composition. And then at the very top level, the record into which we place the composition gives us the patient context. So the record has a patient identity, and that gives us the patient context. So if we take that view, then actually what we see is that, roughly speaking, the alternate levels in the ISO 13606 model give us context from the patient-centered record point of view, and the other levels, so the cluster, the section, and the folder, are just used for organizing the information from the clinical user's perspective. So folders make it easier for clinicians to organize into, say, episodes of care or clinical specialties, but they putting a particular composition into a folder doesn't add any extra clinical meaning. Similarly, sections in a composition give some way to organize the information for the reader of the composition, but they don't convey any particular clinical significance, or rather, in the world that I work in, I don't allow them to have clinical significance. You could argue that the point that if you put a certain collection of entries together in a section, you could make it have some clinical significance, but I think it's better if it doesn't. And the same with clusters. If we organize elements together to make them easier to read, perhaps in a table or a particular layout, then there shouldn't really be any clinical significance in how the elements are organized at that level in a cluster. You could try and create it so, but I think it's better not to. So the alternate levels of the organization to make information more digestible to clinical users. But if you take the information out and reason with it, particularly, then those levels of folder, section, and cluster have no clinical significance. So that's one standard for structured healthcare information, which started towards the end of the last century and became majorly international standard in 2005, with some pre-standards work, particularly from a European perspective, sort of around almost exactly the turn of the century, actually in 2000, the first pre-standard published. More driven from the US is the HL7 Health Level 7 initiative, which started in the late 1980s and started as a messaging standard with not particularly structured information, so using edifact messages and no particular underlying architectural model, until the mid-1990s, when version 3, there basically wasn't a version 1 of HL7. The version 1 was a sort of ad hoc bit of messaging for a year. Version 2 was edifact data messaging. Version 3 started with a complete rework of the whole thing by creating a reference information model, which is an object model which contains everything that you might need to model information in healthcare, and a process described of how to constrain the model down from that all-encompassing model, constrain it for a particular domain, and then into a particular application in that domain, down to a particular message that you might want to pass back and forth to convey information in a particular clinical context. So the HL7 clinical document architecture was the very first HL7 standard to go through the process of starting with the reference information model and constraining it down into effectively a message. So release 1 was around about 2000, and release 2, which is the version that everyone's using now, was from 2005, and the two releases actually quite significantly different. So really it was only with the second release in 2005 that we got to proper structured coded information through the clinical document architecture. So the scope of HL7 CDA version 2 2005 sort of looks a bit like this. So it's an XML standard in the sense that it has an XML representation of the structured information presented in a clinical document. And the clinical document can have a non-XML body, so any representation of the unstructured information in the record, or a structured coded body, or both at the same time. The clinical document corresponds almost precisely with the ISO 13606 composition, and the various points in the structure and the structured body also correspond almost one-to-one with the elements of the ISO 13606 model. And as you can see on the right-hand side with those little snippets from a paper by Dolin, Alschuler and co. From 2005, that this isn't a coincidence. So when they were developing the CDA release 2, then they were heavily influenced by the existing ISO 13606 standard and the activities around structured records coming from Europe. So the fact that there's more or less a complete correspondence between HL7 CDA and ISO 13606 isn't a coincidence. Now, in my opinion, the HL7 CDA structure is a more convenient way to hold clinical information, and then because it corresponds with the ISO 13606 structure, not 100% but pretty closely, then it's possible to make systems which combine the two together and basically hold structured electronic health record in CDA format, and take advantage of the fact that the structure in a CDA document has particular uses for your health record in a very practical sense. So the information in the header sort of corresponds to the information you want in the patient label in a health record system. And in fact, it does, and there's generally more information in the label than there would be in the header, but that's the general sort of gist of what's in the header, the sorts of things you put in the patient label. If you're making different renditions of the structured information, so maybe you're printing off PDF copies of the record for print, or you're generating word processing documents to make letters from, then you're making unstructured or semi-structured renditions of the structured information in the record, which you may want to associate with the structured information, because, for example, if I'm making a structured form-based information and then turn it into a word processing document to make a letter, then the chances are that the word processing document gets edited before it gets printed and sent off somewhere. And it's useful to hold some association between the fully structured version and the rendition, perhaps in a database. But if you start passing the total information around in messages or documents, then you can embed the rendition in the unstructured body of the CDA document in order to make an exchange. The information in the structured body, as I say, more or less corresponds 100% to the ISO 13606 model, even to the extent that it's split into sections, same naming convention and entries. It then diverges a little bit in the terminology. So elements in the ISO 13606 model are called values in the CDA model, and there's no direct way of modeling clusters in the HL7 CDA model. But that aside, the structured body is really the stuff that you're making forms from in a form-based interface. So the structure in the form comes from the structured body, and all the information in the structured body can carry clinical coding. So in that health record system that I showed near the beginning, where we were able to identify all the structure from the ISO 13606 structure, so simultaneously we can see the HL7 CDA documents that lie behind it. So every view which has clinical information in it, the clinical information is held as a CDA document. And if you're running it in a sort of debugging educational mode, you can see the HL7 CDA structures which lie behind every form or view that's in there, and you can see that the structured XML format is there. So this system and others are examples of model-driven electronic health records, and the model-driven health record are the two-stage or multi-stage vision of modeling is what lies behind the OpenAIRE and the ISO 13606 activities. So the reference model in ISO 13606 actually, in my opinion, is an architecture. It's an information architecture rather than a model. And from that architecture, you build models. So in ISO 13606, the models are called archetypes and templates. That information model for a particular domain corresponds more or less to the process you go through in HL7 CDA to go from the RIM, the reference information model, which, by the way, is also an architecture, in my opinion, rather than a model. But as you constrain the RIM in HL7 CDA, so you arrive at an information model, which is equivalent to an archetype or a template in ISO 13606. So the process that we go through to make the health record system that you've seen a couple of pictures from is to start with an information architecture, so those underlying building blocks of models, construct the model for a particular clinical scenario, and then from that generate a system configuration into which we can enter data into the form or pass messages around between different clinical systems. So it's a multi-stage process from architecture to model system configuration to the actual data that appears in the health record. Now, unlike the HL7 RIM, which is an object model, or the ISO 13606 reference model, which is also an object model, the models that we use for architecture are based on ontology. And there's a number of reasons for this, but one of the reasons is that by using ontology-based models and data structures, then the information that we get back at the end when we've recorded health information is much more readily usable as structured information for feeding intelligent systems. So we get away from having to work with unstructured data for as the basis for our reasoning process. So the best definition of ontology, in my opinion, is Tom Gruber's an ontology as an explicit specification of a conceptualization. So conceptualization being an abstract model of the real world, and an ontology is an explicit specification of it. So a defined and explicit way to write down conceptualizations of the real world. And the key to making ontologies is that the explicit specification gives us a common way to model any conceptualization, rather than, as we've started with, say, HL7 reference information model, constraining the conceptualization right from the start. So saying, here's a big model of healthcare, and you can only have conceptualizations that come from that model. Whereas with the ontology view of the world, you sort of flip the world on its head and saying, you can have any conceptualization you like, just when you make it, when it's formalized explicitly, just formalize it in the same way as everyone else, then we can compare the conceptualization. So it's a much looser and freer way to represent models than constraining the constraint-based modeling, say, of HL7. So using ontologies, instead of using the HL7 RIM or the ISO 13606 reference model, we can make an ontology model of the structure of our health record, and there's a bit of it. So starting from the left-hand side in the top corner, we've declared a class which is an entry. Now it's an ISO 13606 entry, so our ontology model is actually an ontology model of the ISO 13606 reference model. So it's not 100% free of ISO 13606. In fact, it's completely referenceable back to it. Then we can make entries, specific named individuals. So the bone mineral density data is an entry in that model, and our particular DEXA scan results are described as being a BMD data entry. And we can describe the elements and the content of the model. So just a tiny part of that ontology model. So a typical model might be several megabytes of ontology describing the particular clinical domain, but on the basis of the ISO 13606 structure, and indeed taking some of the other references from the HL7 world as well to combine them into an ontology model of a particular clinical domain. If I was to write that, there's a tool called Protégé from Stanford, which is where Tom Gruber was originally, which is the sort of go-to tool for making ontologies. And actually, when we started this sort of work just over 10 years ago, that what I'm describing today is based on, we started using ontology to make the information models for the CityHR system. And that was such a dumb idea that it didn't last very long, basically. So I had a master's student who was doing a 3-month project to make a model with Protégé, and after about a morning's work, she just told me it was going to be impossible, and so it was. So better, you could make these models in a spreadsheet. So you can take a spreadsheet, constrain it so that the sheets in the spreadsheet correspond to things in the ISO 13606 and on ontology model, like entries, clusters, elements, sections, compositions, etc. And you can share sections, for example, between compositions, entries between sections, elements between entries, which is the sort of templated approach to HL7 CDA and ISO 13606. You can achieve all that in the spreadsheet. And because spreadsheets these days are actually structured XML documents zipped up to make Office document formats, you can unzip the spreadsheet, process it using standard XML tools, and generate your megabyte sized ontology from the spreadsheet, which is a lot easier than using tools like Protégé. So that's describing making structured health records. We started with Henry Plummer at the Mayo Clinic. I just finished this section with a study from 1968 at the Proceedings of the Mayo Clinic, describing how patients turning up to a clinic were able to fill in a questionnaire using a light pen, fill the questionnaire, but by the time they went into the consultation, the clinician had the results electronically of their questionnaire in front of them and used that to drive the consultation, which is the sort of thing we wish we could do now, except this was 1968. So basically everything we're attempting to do now is catching up sort of 50 years ago, Mayo Clinic. Right, so now we get to having made structured electronic health records using ontologies as the basis for holding the record. both in structuring it and, if we want to, deriving from the recorded data and ontology, then what can we do with it? So I'm only going to have time to show you probably one, possibly two things we can do with it. But here's the first one. So we start with clinical coding. So for many people, the concept of clinical coding, so making a taxonomy of terms and giving each term a unique code, so that we've uniquely identified a concept, and then specifying relationships between concepts. For many people, that equals ontology. So a coding system like SNOMED, which will have a series of defined concepts with their clinical codes, we can view as an ontology. And in fact, you can get representations of SNOMED, which are also in ontology formats such as OWL, the web ontology language, which we just saw a few slides ago. So there's plenty of sources of clinical coding around. There's a few issues, or more than a few issues in clinical coding. And the first one comes here. If we're making a model-driven electronic health record and we're giving clinicians the freedom to model the information that they want to model themselves, ideally in a structured way, reusing templates and archetypes, but essentially gathering the information that they want to gather, then if we give them that freedom, which in my opinion we should, because it's very powerful both for gathering routine clinical data and for research purposes, then what we don't want to do is constrain them to a particular model. So we don't want to constrain them 100% to the HL7 RIM, but neither do we want to constrain them to the SNOMED ontology of clinical terms. Okay, it's got 1.5 million terms in, but there's many expert clinicians who disagree with the way that ontology is constructed in SNOMED, who may have differing opinions of how information should be structured in their particular specialist domain, may want to do things quite fundamentally differently from the coding structures that are available to them. So we have this prospect always, if there's any model-driven development, that there will be concepts in the clinician-developed model for which there is no clinical code available in any publicly available coding system. And yet, because we have a highly structured health record, every single concept in that record, from the very top level of the health record itself, through the folders, the compositions, even the sections, clusters, the thing which don't necessarily carry clinical context, each of those is uniquely identifiable as a code point in the information that we're gathering. Whether there's a SNOMED code for it, or a LOINC code for it, or an ICD-11 code for it, or not, or whether there's actually codes which there's an ICD-11 code and a SNOMED code, or there's some grey area where it's a partly overlapping concept falls somewhere between overlapping concepts in some of the coding systems. The fact is that if we've developed a structured model, everything in our model is uniquely identifiable to us. So in the CTHR, that health record system, everything is coded not to a particular coding system, but to the CTHR code, because we know that everything is identifiable in that coding. So here is the code, which is the HL7 CDA representation of coding, which has the code system, in our case CityHR, and the display name. That's the standard way of holding the clinical code in HL7 CDA. Now that's great inside the CityHR, but when we want to exchange that elsewhere or run some reasoning engine over it, then that's not very useful. So internally for us, then we can uniquely identify each concept, but externally we're not in the business of making a new coding system. Externally, we do want to exchange using Loink or SNOMED or whatever. So we have a representation to allow us to map from the uniquely identified concepts inside the structured health record with any coding system, which means that the coding can be applied retrospectively if the coding system changes. So if ICD-11 replaces ICD-10, then we can apply a different set of codes. If new codes get added to SNOMED, we can include them. If we want to generate coding just for Loink or just for SNOMED, we can do that. So we're not tied to any particular coding system, but we can make the mapping as required. And that model of how to map the code points in CityHR to any particular coding system is itself held as an ontology. So we have an ontology model of clinical coding, and because we have an ontology model of what's essentially an ontology, then we can reason, if necessary, inside the coding ontology. I've never tried to do that, but you could potentially reason about the ontology, because the ontology is conceptually modeled as an ontology. So we have an ontology model of coding. And just in the same way that we use spreadsheets to make the structured health record model, so make the ontology model of the structured record, so we can use spreadsheets to make the model of our code mappings, so mappings of our code points to any particular coding system. So here we're saying that the body mass index entry is mapped to particular SNOMED codes, but we can also put some reasoning or conditions on exactly how those are mapped using the relationships between any of the concepts, which are all uniquely identifiable in the model, in how we apply the codes. So having made that in a spreadsheet, we then get a set of structured records with whatever coding system applied to it, whether it's SNOMED, Loink, or ICD-11 or whatever. And then we can make our first step to doing something useful with our structured health record. So one quick win is just to link coded electronic health record data with coded knowledge sources. So if I extract the terms from that sentence there, then I can pull out codes, and maybe if that was a guideline, I'd have done some natural language processing to extract those terms from it, but then I can code them. So I can get a reasonable coded description of what that paragraph there is saying if I apply codes to the key terms in it. So to connect my structured health record with whatever knowledge I want, then all I need to do is have a structured health record where every part of the structure carries clinical coding, and find some way to clinically code the knowledge sources that I think might be useful to associate in some way or other with my health record data, and where the overlap occurs between the coding. It's a little bit more sophisticated algorithm than just whether there's a matching code, but where those correspond to each other, then we can have a reasonable degree of belief that the knowledge as coded is relevant to the coded clinical information. So where are these knowledge sources? Well, they're all over the place and anywhere. So let's, for example, pick some videos on YouTube about osteoporosis. So there's 4 there, which were found a few years ago. We can find those, and there's information everywhere on the web. So what Tim Berners-Lee likes to think of as becoming the semantic web. There's knowledge everywhere, and vast amounts of knowledge available on the web. And thanks to the World Wide Web Consortium and activities from around the turn of the century, we have an open standard for making the connections between any addressable resource on the internet and essentially applying metadata. And that standard is called the Resource Description Framework, so RDF. So we can make an RDF knowledge map where we're describing any addressable resource, so like that, some pathways in this case, with the metadata which is attached to it. So in this case, we're SNOMED coding resources here, which are care pathways. And the key thing about the RDF knowledge maps is we don't have to even have access to that. We don't have to embed the coding in there. We don't have to be the owner of that resource. We just need to be able to address it. If we can address it, then we can code it. And we can do that through some user interfaces in the health record system. We can basically specify our coding system, what code we're using, a descriptive display name, and the URL, the addressable resource anywhere on the internet that we want to be coding. So if we find our YouTube video, get its embedded URL, and start coding away, then we can associate that with any part of the structured content that we're gathering in our clinical record. And so just by making the association between clinical codes, we can start to deliver information at the particular clinical context to what we're currently interacting with the health record. So in this case, 2 things delivered at this particular point when we're talking about bone mineral density and DEXA scans. One is a video about the common signs of osteoporosis, which we seem to have here with the t-score of -2.5 is the definition, or -2.5 or less is the definition of osteoporosis. So this is definitely relevant here. Or this was the clinical guideline from the National Institute of Clinical Excellence, which is relevant to osteoporosis and its management. So what's happening there is this, as just to summarize what I've just been talking about there, is that we take a set of knowledge resources anywhere, any addressable knowledge, and we build a knowledge map using RDF. We're effectively clinically coding knowledge which is available on the internet. Then in the patient record, we have the structured view, which, whereas I've mentioned, every part of the structure, all the information in the structure is addressable within our own internal addressable coding view, and then all we then need to do is to get a recognized clinical coding system like SNOMED or LOINC or whatever, and dynamically apply the clinical coding to the view that we have. So we can inject coding into the view and then have some matching algorithm, which can be as naive or sophisticated as we like, which matches with the knowledge map. And having made a match, then we have the addressable resource in the RDF triple. We retrieve the knowledge from its addressable resource on the internet and deliver it into the supporting knowledge view inside the health record system. By coding knowledge in different ways, so for example, we could in our knowledge map code based on health literacy, for example, we can spare the expert rheumatologist a video on the signs of osteoporosis. But if we have a patient viewing their own record who knows nothing about osteoporosis other than they've got a painful back, then we can target the knowledge or deliver knowledge at the appropriate level if we've included coding about health literacy of the user of the system, be they patient or expert clinician. So that's our first place that we could match our structured health record with the start of some AI techniques, which just about coincides with me running out of my hours time. So let's see how far we get. I'll just keep going for a few more minutes and then I'll stop. So a few useful things to say. We started with the move from data to information by putting data into context, in particular talking about the clinical statement to make useful clinical context to make information, so useful clinical information. Most of us are familiar with the next step of putting additional context to the information so that we have information about how to apply, so information with the context in which it should be applied, and then we've created some knowledge. So if the patient has a t-score less than -2.5, they have osteoporosis. Now there is some knowledge. I could learn that knowledge and I could be a very knowledgeable person and I could have absolutely zero understanding, because if somebody says to me, why is it that a patient with a t-score less than -2.5, why do they have osteoporosis? I don't know. If I can't answer the question why, then I have no understanding. You can be highly knowledgeable and very successful without having any understanding of anything. So to move to the next level on this progression described by Russell Lakoff in the actually 1960s, but references from a compendium of his work. If I move to the next level of understanding, I am able to answer the question why. And then the final step that Lakoff takes is from understanding to wisdom. So his definition of wisdom is that when we use understanding to apply knowledge in a particular context, then wisdom comes with knowing the value of applying that knowledge. So as soon as we have an appreciation of the value of the knowledge we're beginning to a particular scenario situation, then we're able to make wise decisions rather than just making decisions based on knowledge. So there's a whole spectrum there of from data to wisdom, and the bit in the middle of understanding is where there's the gap, between a lot of the AI which goes on now and which has been growing very usefully in terms of pattern recognition and machine learning for the last 10, 15 years, and where you can get to if you're feeding the AI engines, the reasoning engines with structured knowledge, because we may recognize a word or a face or a lesion or a fracture on a diagnostic image, and we might be highly accurate in doing that, but we don't know why. When we ask Alexa to play our favorite tune and it's made those sort of pattern matching, Alexa has no knowledge of why it is that it's playing that tune. It just knows it's matched all the words that I said. So by feeding our AI reasoning engines with more structured knowledge and using some other types of techniques like Bayesian inference, for example, then we can start to understand enough to answer the questions why. So I'll just keep going for a minute or so and going back to rules-based reasoning. So just about the first realistic expert systems in the 1970s, the early 70s, came from rules-based reasoning based on the progression which started with Alan Turing in the late 40s and 50s on why can we make intelligent machines? Can machines think? Through the what used to be called the Dartmouth Conference, now the Dartmouth Summer Research Project on Artificial Intelligence. All of that work sort of culminated in the first generation of expert systems in the early 1970s, which started to make decision support systems rather than decision making systems. So the delivery of knowledge into the context that we spoke of just now is helping clinicians make decisions rather than making decisions for them. And so recommendations based on rules-based inference allows the a recommendation to be made, but also allows the clinician to ask why. And if you're providing decision support in terms of recommending what's to be done, then to be able to answer the question why, that you don't prescribe this drug. Why? Because there's interactions or contraindications, and that's come from our knowledgeable drug dictionary. We're able to ask why, and maybe once we know why, we're able to make our own decisions independently of the advice that we've been given. I think I'm going to stop. So the things which you haven't talked about is
Thank you,
lots.
John.
But we've run out of time. So if we had another 2 hours, I'd keep going.
Don't worry,
as Abdul well knows.
we can continue a bit later on. But for those people who had only fixed themselves up for an hour, and I think about 25 of them left after 11 o'clock. But anyway, there are a few people around that still. If they have any questions to ask and any thought to share with us, with John, then please do so. This is your chance. Anyone?